Okay, so the next paper we're doing is 2021 January Physics International A-Level Edexcel for Unit 2 Waves and Electricity. Okay, so we'll go straight into it. Start with the multiple choice. So the first question is about the unit of power, being the watt. Well, 1 watt is 1 joule per second, and 1 joule per second is 1 Newton times 1 meter divided by a second. A Newton is kilograms meters per second squared, and multiply the Newton by meters per second, you will get the base units which this question wants you to think about. So newtons is kilograms meters squared, kilograms meters per second squared. If you multiply by the meters per second outside there, you will get kilograms meters squared seconds to the minus 3. Okay, so that's how you work out what a watt is in base units. These are the base units you will meet in the first year of A-level, kilograms, meters, seconds and amps, and then in year 13 you will meet Kelvin and mole and maybe the intensity of light, but so there are 7 in total, but normally we don't use the intensity of light very often. Okay, so Newton is definitely not a base unit. A joule is not a base unit. So an amp is a base unit but does not feature in kilograms meters squared seconds to the minus 3. So the question is actually asking which of the following is included in the SI base units for power. Well, this is the SI base units for power. SI base units for power are these. Okay? If you don't know how to do these, you need to practice. Okay? So the only one that comes into it from the list is kilograms. Okay? Part 2. The diagram shows a combination of 3 resistors. Resistances X, Y, and Z. Okay, so 2 of them are in parallel, 1 of them is in series. So first you've got to work out the resistors in parallel, RP. So RP are Y and Z, so 1 over Y plus 1 over Z is going to be the resistance of the combination. Okay, then the total resistance will be Rx plus whatever the algebra is for the resistors in parallel. Okay, well the Rx is just X, so you add it in to what this is. So 1 over Y plus 1 over Z, you need to inverse it because this is on the bottom of the fraction, so it's to the power of minus 1. Well, if you know how to do that, you multiply the denominators by each other, so Y over Z, yeah, and then that would become cross multiply, this will be a Y and this will be a Z, so Z plus Y over YZ is how you simplify that, but you want the inverse of that, so you have to reverse the fraction. So it becomes YZ at the top and Z plus Y or Y plus Z at the bottom. So the only answer is this. So you need to know how to do this. You need to know about resistors in parallel, how to transform such fractions. So you need to be able to do that from maths. And when you do that, you'll see the answer is C. Oh, I haven't shown you the answers clearly. I apologize. Okay, so I'm zoomed in, so I need to make sure I do that. So this is how you do it. 1 plus Y plus over 1 plus Z, inverse it. You want to get what is the parallel resistors, and that's how you do it. Okay, you cross multiply. The denominator becomes YZ, so the Z plus the Y is correct. You just got to make sure you know this mathematically. Okay, the only answer is C. Question 3 is about ultrasound. Ultrasound can be used to investigate organs inside the body. Which of the following statements is correct? All of the ultrasound is reflected at the boundary. Well, that's not true. Some of it will be reflected depending on the density of the tissues. Okay, so for example, more will be reflected if, for example, if it's a dense tissue like bone compared to soft tissue. Ultrasound travels faster in air than inside the body. That's wrong because sound travels faster in denser medium. It's not like light. And the answer, the third one, is ultrasound with a greater wavelength gives an image with a higher resolution. Well, no, you need to make sure you know about resolution. If the wavelength increases, the frequency goes down. And if the frequency goes down, you're going to get a less clear image. Okay? You need to make sure you research how the resolution of ultrasound images. What does it depend on? Well, it depends on the frequency. You want a higher frequency, which gives a sharper image. So D is the correct answer. Ultrasound with a shorter pulse duration means the period is smaller. So you may have done this in an oscilloscope. A small period means a bigger frequency. Okay? So it means that the waves will be sharper. There'll be less duration of each one. So the peaks will be more pointed. Gives an image with a higher resolution. So this is correct. Small frequency equals high frequency. Small t equals a high frequency, which is a sharper image. I recommend just doing some research on the resolution of ultrasound for your own benefit. Okay, question 4 is about electromagnetic radiation. Yeah, in terms of the photon model. Okay, so which of the following demonstrates the photon model? Well, the answer is C, photoelectric effect. All the others, diffraction patterns, Huygens construction, which is using wavelets to create constructive and destructive interference patterns, is using a wave model, as is plane polarization. So polarization is something that is explained using the wave model. So A, B, and D are the wave model. Only the photoelectric effect is demonstrates the photon model for light. Okay. Question 5 and 6 are using this internal resistance circuit diagram. So what happens in such a diagram? You have the battery, which has its own internal resistance inside it. So you can imagine this is your Duracell battery or whatever you buy. There's the positive terminal. This is positive, and this is the negative side. So this is the base of the battery. So the battery kind of looks like that. It's as if the 1.5 volts or whatever it is, the EMF that you get through the battery that you buy in the shops, for example, is actually a cell, because it's a unit, one single unit. It has its own internal resistance inside. So you've got an internal resistance and an external resistance in a circuit. You can measure the voltage that the battery is providing. When there is no current being drawn, you will measure the maximum value of the battery's EMF. But as soon as you draw a current, the current goes through, and you can measure the current. It also goes through here, so you'll get some current going in, so whatever that current is, and obviously I times R becomes lost volts inside the cell itself. So that's the concept that they want you to be aware of, and this is one of the core practicals. I can't remember if it's 7 or 8. Okay, this is something you need to look at. You need to make sure you know how to do this investigation, so you can change the resistance externally. That will adjust the current, and that will show how much you lose from the EMF in terms of the lost volts. Okay, so corresponding values of potential difference and current were taken after adjusting the variable resistor. So that's what it's there for. A graph of V on the y-axis here, and against I on the x-axis was plotted. Okay, you're going to get a graph that goes downwards from the EMF. The more current you put in, the more of the EMF you lose. So this is called the terminal potential difference, what the voltage is measuring. So it says, which of the following is correct? The area underneath the graph is the total energy dissipated in the cell. Well, if it would be the area under the graph, you're actually multiplying voltage by current, so it wouldn't be energy. Voltage times current would be power, so that you can see that's wrong. The gradient of the graph is R. Well, that's close to the right answer, but in fact it's a negative gradient, so it would be minus R. And so be careful with that one. The graph shows that V and I are directly proportional. Well, no, they're not directly proportional. Directly proportional means going up this way, yeah, in proportion. So you double the current, you'll double the voltage, and so on. And the y-intercept of the graph is the EMF. Yes, so it starts with the zero current, you get the full EMF. As soon as you draw current, the EMF drops, and you get a lower operating voltage. Okay, so question 6. The resistance of the variable resistor in the circuit above is R. So I've drawn that on the circuit. The resistance is R here. Which of the following gives the current in the cell? Okay, so I've worked it out for you. The current in the cell can be derived by looking at Kirchhoff's second law. Kirchhoff's second law states that the sum of the EMF, well in this case it's just E, there's the sum of the EMF when you have 1, is equal to the sum of the potential differences in the circuit. Well, there's two places where potential difference is lost. You lose some potential difference is used in the external variable resistor, and as I explained to you at the beginning, you lose some potential difference internally in the battery once you have a current flowing. Okay, the only time you don't lose any voltage is when the current is 0. So the EMF will equal to the V in the external resistance plus the V lost in the internal resistance. The current is the same for both, so you can change VR to I capital R and I little r, which is the resistance shown inside the cell. So the EMF will be equal to I, take it outside, and bracket the R plus the little r, make I the subject of the formula, and you'll see that the answer is C. Okay. Question 7. A graph of displacement against time for a transverse progressive wave is shown. Yeah. So remember, for waves there are two types of graphs: displacement against time and displacement against distance. So you could have a displacement against distance here. So the wavelength, for example, in part D cannot be obtained from a displacement time graph, because you want to know the length of it. So you want to know, so if this was a displacement distance graph, then the peak to peak would be the wavelength, but this is in seconds, so it's the period. Okay, so D is definitely wrong because it's the wrong graph to be able to measure it. The amplitude of the wave is 20 centimeters. Well, they're just, you can work out the amplitude. Amplitude is the maximum displacement, yeah, from the central position. So here is the equilibrium position. So the equilibrium position, the amplitude is 10 centimeters away from the equilibrium position. In other words, if you stop the disturbance of the medium, whatever this wave is traveling through, it will go back to the 0 point. Okay, so it should be 10 centimeters, not 20. And then the frequency of the wave is 2.5 hertz. Well, first we need to be able to calculate that, because the period is 0.4, so C is wrong. The period is not 0.2, that's half a wave. From there to there is half a wave. From peak to peak would be a full wave. You know the period is 0.4 seconds. Once you know the period, you know F equals 1 over period. 1 over 0.4 is 2.5, so the answer is B. Question 8. A ray of light travels through glass towards the boundary between glass and air. So it's traveling through the glass towards the air. The critical angle for this boundary is 42 degrees. So it's like you have a ray that's coming in. Here's the normal. So the ray is coming from this angle. And if this angle here is greater than the critical angle or equal to the critical angle, it goes this way. Yeah. So at C, remember, so it's going from the glass, and here is the air. It will go along the boundary at the critical angle. So this is something that you do in GCSE, and then they ask you about it in more detail at A levels. So which row of the table is correct? Okay. Well, these angles are less than 42 degrees. So you at less than 42 degrees, you'll get some of the light going through, and some of the light will reflect. So you'll get some partial reflection and partial refraction. So these two are both wrong, because it says all the light is refracted. No, there's always going to be some reflection at the boundary. Okay, And all of the light is reflected is not true because it's less than 42 degrees. Some of it will get through into the air at less than 42 degrees. Okay? And so it should be C or D, 45 degrees, but it says 45 degrees, all the light is refracted. No, at 45 degrees, because it's greater than 42, you're not going to even get it along there. You'll get total internal reflection because the angle here is greater than C, the critical angle. So it leads to total internal reflection. That's question 8. Okay, question 9 is about de Broglie. De Broglie is the one who came up with this equation so that particles have equivalent wavelengths, or effective wavelengths. So the wavelength of a particle can be determined using Planck's constant divided by the momentum. So this is the equation. They want you to know which of the following is correct. The de Broglie wavelength is independent of the mass of the particle. Well, that's not true because the mass of the particle is included in the momentum. So P equals mv, so A is wrong. The de Broglie wavelength can be used to calculate the momentum of a photon. Well, that's correct. You can. For a photon, it can be used because you know h, and if you know the wavelength of a photon, you can work out its effective momentum. Okay? So you could say photons have effective momentum. The answer is B. Let's just go through the others too so you can revise them. The term P represents the mass of an electron multiplied by the speed of light. Yeah? Well, the electrons don't go the speed of light. Yeah? If they did, it would be correct, but the electrons have their own speed. So P is mv, not mc, if you like. The value of h depends on the particle involved. No, h is a constant. It's Planck's constant and is given to you in your data sheet. Question 10, you have a series circuit where you have 3.1 times 10 to the 19 electrons passing a particular point in a time of 30 seconds. So T is 30 seconds. Q is the number of electrons times the charge of the electrons will be able to give you your charge in coulombs. Okay, I always teach my GCSE students that you need 1.6 times 10 to the 18, 1.6 times 10 to the 18 electrons will be equal to 1 coulomb. Okay, you can work it out based on the charge of an electron. So that's the number you require to get 1 coulomb. Well, you got more than that. Yeah, you got 3.1 times 10 to the 19. So if you know that I is, they want you to find out what is the current using the data they've given you. Well, current is coulombs per second, charge divided by time, and the charge is n times E. So this number times the charge of 1 electron divided by 30 seconds. So it's 3.1 times 10 to the 19 electrons. Each one has a charge of 1.6 times 10 to the minus 19 coulombs. Divide that by 30 and you'll see the only equation which is correct is in question 10 is A. Okay, that's the multiple choice questions done. We're going to bang on, keep going, because the section B has 21, it goes up to question 21. So we'll do a few of the short questions first and then we'll stop, take a break, and I'll do the second part of section B later on. Okay, so here we have a copper wire. The radius is given and carries a certain current, so the I is 5.1 amps. Calculate the drift velocity. As soon as you know its drift velocity, you need to use this equation. So there's the drift velocity. We want to calculate V. We know E. The A is being given here, and the N has been given here. The A is calculated using pi r squared. So there's the A if you calculate it using the distance you're given. So that shouldn't be there. It should be the N. So the N is given to you. Put the numbers in and you'll get 7.5 times 10 to the minus 4 meters per second. Stop the video if you don't follow it at any stage. I also like to advise people watching, you can watch it at 1.75 speed and you can get through it more effectively, I think. You don't need to listen at the normal speaking speed. I myself, when I listen to my videos, I put it on 1.75, and then you can pause the video when you get confused. So here, student investigated the superposition of water waves in a ripple tank. Superposition means when you add one wave to another wave, for example, there, if they're in phase, they'll constructively interfere. There are two sources of waves, S1 and S2, okay, which are in phase, it says. Okay, the diagram shows the positions of successive crests of each wave at an instant in time. Okay, so over here you can see, for example, A goes through all the points where the two waves come together, the peaks arrive together. That means A will also be a position where in between the waves the waves are in phase. Okay. Alright, the diagram shows these successive crests, so you could say these are wave fronts looking at it from above. Okay. Explain the type of superposition taking place at position A and position B. So I've already drawn where the lines cross are lines of constructive interference. So for position A, you can see it goes through one of those lines goes through A. So position A, yeah, you've got to explain the type of superposition going on at both A and B. So then position A, there's constructive superposition or interference, constructive interference, when waves from S1 and S2 arrive in phase. Okay, so a peak will arrive with a peak and a trough will arrive with a trough along those lines. Okay, and here we have destructive at B, which is halfway between the two lines I've drawn through A and one through the other side of it. B is halfway between them, so you'll have destructive superposition or interference, destructive interference, when waves from S1 and 2 arrive. They're out of phase by a whole number of half wavelengths, okay? The peak from S2, for example, here, and meets a trough from S1, okay? So this one's come from S2, this peak, and there is halfway between the peaks from S1. So peak from S2 meets a trough from S1 for position B. So S1 is out of phase actually by 1.5 wavelengths if you actually count the number of waves that have passed. Sorry, I'm not showing you my writing. I keep on making this mistake. So I'll just put that and you can see what I was talking about. Okay? So again, position A, they're in phase. They arrive in phase. And for position B, they're halfway. You can see 1 is on a peak. And from S1 is halfway between the S1 waves. 1, 2, 3, 4. So between 3 and 4, third and the fourth crests from there. So from here, 1, 2, 3, 3.5 waves have gone by here. 3, and you're on the trough. From S2, 1, 2, 3, 4, 5 waves have reached B. So 5 crests from B, from S2 have gone there, and only 3.5 from there. That means this one reaches there as a peak, and this wave comes here as a trough, so they're going to be destructively interfering, and that's what the words say. Okay? Hope that makes sense to you. Whereas if you look at S1 and S2 for A, let's just do that. 1, 2, 3.5 waves from A, and from B, 1, 2, 3, 4.5 waves. So they're in phase. Okay? So from S1, it was 3.5 waves, and from S2 is 4.5 waves, or wavelengths, have passed. So these are in phase because it's only the difference, path difference, yeah, is equal to a full number of wavelengths. And over here, the path difference, yeah, for S1 is out of phase by 1.5 wavelengths, so it's an odd number. So that's what you've got to look for. Odd number of half wavelengths becomes destructive interference. Okay. Okay, so that's 11 and 12 done. Question 13 is showing you a 5 kilo ohm resistor in series with an LDR. So you're basically dividing the EMF between these two resistances. So students investigating how the light intensity, this represents light coming in, affects the resistance of an LDR. Okay, so I've just labeled it LDR for the ease of the question. She set up the circuit using a cell with negligible internal resistance, so we don't want another resistance affecting the calculations that you may have to do, as shown. So we're ignoring the fact that there is in fact some internal resistance. It then says the EMF of the cell was 1.5 volts. Yeah, so this is the EMF of the cell. So there's EMF equals 1.50 volts. When the lights in the laboratory were switched off, in other words when it's dark, the voltmeter reading here was 1.19 volts. That means that the LDR would get the rest of the 1.5, so the LDR, when it's dark, the LDR would get 1.50 minus 1.19, because this is taking 1.19, so it gets 0.31 volts when it's dark. Okay, calculate the resistance of the LDR. So we first need to work out the current in this circuit, and you know for current in a series the current's the same everywhere. So we know that this is 1.19 volts here. We know the resistance is 5,000 ohms, so we can work out the current just using this resistance and this voltage. That gives you the current of 2.38 times 10 to the minus 4 amps. Okay. Then the voltage of the LDR, as I told you, is 0.31 volts. Once you know this 0.31 volts divided by the same current, and you'll get that the resistance of the LDR in the dark is 1300 to two significant figures. I think it comes to slightly just above that. Okay, the next part of the question is asking you, when the lights were switched back on, the student discovered that it was impossible to calculate the resistance of the LDR using this circuit. So the reason he's saying that is the teacher said with the lights on, the resistance of the LDR is about 9 ohms. I don't know how a teacher knows that. He must be given the answer. So if that is the R of the LDR, 9 ohms, then we know that the LDR with the lights on will get 9 out of 5,009 total parts of the resistance, because the total resistance in the light will be 5,000 ohms here and 9 ohms here in the light. So the total resistance is 5,009 ohms. So the LDR will only get a very small fraction of the total EMF, so it'll be 9 out of 5,000 of the 1.5 volts, which is the EMF. So it only will be able to get, calculated wise, less than 0.001 volt, just less than 0.01 volts. So that means it's a fraction, and the resolution of the voltmeter is 0.01 volts. So the voltmeter can't detect the drop, and it will just read the full value will be across the main resistor. Okay, because the LDR becomes very low resistance, so it's not getting its share of it. So once you work out that this is much less than the resolution of the voltmeter, which is 0.01, that's one mark. You then say this would indicate that the resolution of the voltmeter is insufficient to detect the small voltage or potential difference across the LDR, where it's not across the LDR, is it? But if you put a voltmeter there, you wouldn't be able to detect it because it would be less than 0.01 volts. You could also say it would be insufficient to detect the small potential difference drop in the voltage across the 5 kilo ohm resistor. In other words, a voltmeter which the way it's set up on this circuit diagram will read the full EMF, which is 1.50 volts. Okay, so that's, I hope, clear enough for you. So that's question 13. Question 14, this diagram shows energy levels for hydrogen, the atom. So this is the ground state, and this is when you can escape from the atom. So that's if you get 13.6 electron volts, you can make the electron escape, in theory, reach the freedom level. Okay, so this is the ionization energy, if you like, from there. So when an electron with a kinetic energy of 12.3 interacts with this atom, so this is an external electron, the incoming electron, an electron in the atom here, so the electron is here, it says it will move from this level all the way up to the 1.5 volt level, so we'll jump to there. Okay, so that's an incoming electron that does that, causes that excitation. When a photon with a photon energy of the same value, energy of 12.3, is instant on this atom, the electron in the atom here at the 13.6 electron volt level remains where it was. Explain these observations. Well, for the electron in the hydrogen atom, for the electron case, the hydrogen atom, in the hydrogen atom, it will move from 13.6 electrons to that needed value because it needs 12.1 electron volts. The incoming electron provides this 12.1 electron volts, but keeps the remaining 0.2 electron volts as its own kinetic energy. So electrons can do that because they can just retain some of their kinetic energy. But in the case of a photon, all its energy must be transferred to a single electron. Okay, so that's your first mark. And these two are the 2 marks for the first case. However, this can only happen if the energy of the incoming photon exactly matches the 12.1 volts, electron volts, required to excite or elevate the atom's electron from 13.6 to 1.5. So with photons you need the exact match, but for electrons it can keep 0.2 of its kinetic and 0.2 electron volts of its kinetic energy for itself. I hope that's clear. So this is the quantum nature of photons. Okay, so that's question 14 done. And we'll do one more question and then we'll stop. So physics teacher placed a coin in this cup. When viewing the cup from an angle, the coin was not visible because it's down at the bottom. So you're looking at it from the angle shown in the photograph. While still observing from the same angle, the teacher slowly poured water into the cup. So it might be quite a good experiment to try. The coin gradually became visible. Okay, the effect is caused by refraction. Explain what is meant by refraction. Well, refraction means when light rays change direction. Yeah, obviously when moving from one medium, in this case it's moving from the water into the air towards your eye. So the light rays change direction when it comes out of the water into the air due to the change in the optical density or due to the change in the speed of light in the different media. Okay, so that's how you would get the marks, okay, for the first definition of refraction. Part B, the simplified diagram below shows what's going on. So the light's coming here, theta 2, I put the angle in water as 2, and the angle to the normal. Remember, this dotted line is called the normal. All angles are measured to the normal. It then will bend because of the water that was added in. So when you had no water there, it would just go straight and it wouldn't be seen from the position that they were looking at. Okay. So this diagram is showing what's happening when you have the water in there. It's given you the different heights of the water and the height of the air up to the edge of the cup. Okay. So they've also given you two distances here. Now these distances are given so you can use trigonometry to work out the angles to the normal, both in the air and in the water. Okay. So they want you to determine the refractive index. So to determine the refractive index, you need to know that the refractive index is sine of theta 1 in the air divided by sine of theta 2 in the water. So I'm using the GCSE definition. So this equation comes from n1 sine theta 1 in the A-level version equals n2 sine theta 2. Now you should be able to work out that if you make it sine theta 1 over sine theta 2, then the n2 over the n1 will give you n. So the n2 is this, and the n1 is this, which n1 equals 1.0 for air. So we want to know what is n2. Okay, so that n is the ratio of the denser medium compared to the lighter medium. Okay, so where theta 1 is equal to 3.7 here divided by 4, which is here. So this is 3.7. Here's 3.7. So that would be also equal to, if you join the dotted line up, that will be 3.7 up there. And this is 4.0 here, from there to there. So tan is opposite over adjacent. So once you do that, you'll work out that theta 1 is 43 degrees. And theta 2, you do it in the same way. This time you're using 1.8 over 3.0, which is given to you. And you do that, you'll find that theta 2 is 31 degrees. Once you've got both angles, you can then work out that the refractive index from air into water is 1.32. So that's how you do this question. That is question 15 done. And let's stop there. Question 16 is about comparing filament lamps with thermistors, the graphs. So we'll go through that later. So I'll put that here that you can look at it while I'm talking. You can stop the video so you'll have had time to look at my answers for question 16, and we'll go through it when I do the next video. So thank you for watching. Please share the video with your friends, anyone else who's doing this exam. Like the video so we get more viewers. And if you want to know when the next video is ready, just make sure that you have what's the word? Subscribe. That's the word I was looking for. Subscribe to our channel, and I think you've got to press that bell notification so it will make sure you know when the next videos are. We've got quite a few videos up already for units 1, 2, and we got I think a few for unit 4 as well. So my students currently are doing units 2 and 5, but some want to retake unit 1. So I'm making as many videos as I can to help my students, but while I'm at it, I'm making sure that other people have access to them as well. I hope you find it useful. Remember, this is how to communicate clearly. It's not just being able to see what the mark scheme says. It's how you should lay out your answers in the most clear fashion. Well, thank you very much for watching. That's it for now. See you in the next video.